Recording is rolling. It's Monday, January 12th. So I want to do a Kahoot with you guys on rotational mechanics. And I read the questions, of course, ahead of time, and we've covered most of the content, but there's it's like one or two questions that deal with angular momentum, which I hadn't quite got to yet. So I'll do a little bit of that with you guys real fast. Right, and then if we have some spare time, I'll do some textbook puzzles with you guys. Right? And I still have a lot of postbooks and content that I want to go over, but it'll have to be next few days. That's what we're doing. Right? And so, what is this conservation of angular momentum? All right, so you guys my class. If you guys remember back on Friday, like the last minute of class, you guys had the spike wheel, right, and you get the spin, and then it's acting like a gyroscope, so it's hard to change its orientation. Right, right. So more on that next couple of days. But here's my poster version that's related to that concept. Okay, right, so you guys remember momentum was mass times velocity? Right. And during collisions, that was conserved. Right? You had those collision cards that bam, bam, right? Momentum was conserved. Right. Well, in an angular sense, what takes the place of mass is rotational inertia. What takes the place of velocity is angular velocity, but like turntable turning at some speed. Right? Right, so that product right there turns out is also conserved. Kind of like linear momentum was conserved, but this is angular momentum, and that's conserved. Okay. So some of angular momentum before some event equals some of angular momentum after the event. Okay. And the event could be something like, yes, here's a real classic set. And I think the question on Kahoot is basically this picture. Okay. So Winter Olympics are coming up. You guys seen figure skating before? Figure skating? Yeah, watch this here. Whenever, let's say an ice skater has their arms extended and they go into a spin, okay, and then they pull their arms in, what happens to their spin rate? Yeah, spin faster. Did I show you guys the Paul Hewitt version of this?
It's a very low friction rotating platform. What I'm going to do is I'm going to stand on that platform. I'm going to hold these weights out. When I hold these weights out like this, I'm going to spin like this. When I hold them out far, do I have a lot of rotation inertia or a little? How about when I pull them in? A little? So if I get here rotating like this and I hold them out, what happens when I pull them in? Ooh, easier to rotate, gang. Harder to rotate. Easier to rotate.
Pretty crazy. Oh, there's a it was in the background there. So what you guys just saw was this. So the product of I omega is concerned. Right? Is when he brings his arms in, doesn't his rotational inertia decrease because it's now closer to that rotation axis? Right? So the eye gets small. Right? But in consequence, the angular speed has to increase, so which says he's spinning faster. That's exactly what you guys just saw. Right? So that. Okay. Oh, what about what else can I ask about this? Okay, so how about this? Which system? Okay, so let's take a big picture here. If I ran kinetic energy, which we also haven't quite talked about yet, but that's like 1/2 I omega squared. Something about kinetic energy system. Take a guess. Which one of these pictures do you think has more kinetic energy? Now that'll be different. It won't be the same because what's the same as angular momentum. Right? Okay. Can you guys reason which one must have more kinetic energy? When you spin it slow or spin it fast? Yeah, right. Just trying to spin it fast. Now there's competing effects with the rotational inertia and the angular speed. Right? Now this is to pull your arms in. Can you guys imagine if you were spinning like this, figure skating, and you pull your arms in? Does it take some effort to do that? Right? In fact, the physics word for that might be work. It takes some work to move your arms some distance closer to your body. Okay, so now some energy is transferring from your muscles, that's like chemical energy, into your motion, that's like kinetic energy. All right, so uh, now I think you guys are definitely ready for any of these Kahoot questions. All right, you guys ready to go on Kahoot? Ooh, well, right, you have to jump in as soon as you can. We are going. All right, so this keeps jumping around. Let me fix this.
You know,
Force times lever arm. What is that about? Force times lever arm. You guys remember this torque? Right? Like the turning moment, trying to turn a nut with a wrench, open the doors. My other classic example, this could be the door hinge over here. This could be the handle. Okay? So it's this radial arm crossed with the force. When I say crossed with, that's a special kind of multiplication that pertains to vectors. Is it really means I'm multiplying the what components, the parallel or the perpendicular? Yeah, perpendicular. Right? See if I push perpendicular, I'm maximizing the possible torque. Okay? See if I pull or push parallel to the wrench, this nut's never going to turn at all. Right? If I push on some weird angle, well, I have to take sine of this angle theta, tell me how much torque I get. Okay? So force times lever arm. Right? What else do you guys choose? All right, so guys, all these other options have some votes. Guys, what are these? Guys, what is mass times velocity? Momentum, right? Momentum, MVR. This is actually angular momentum of a point mass. We haven't even talked about that yet. Right? Guys, what is force applied for some time? Force times time. You guys remember that was an impulse, which is a change in momentum. Okay. All right. But force times lever arm, get a torque. I got Anna and Bruce the villain. Ooh. I like to lose to Bruce the villain. It's easier to loosen a nut with a wrench if you what? Push perpendicular, exert a larger force, extend the lever arm, all the above. Yeah, all the above, all the above. Okay. Yeah, you can see all three right here. Okay. So guys, what if the wrench was longer? What if you attach a PVC pipe and extend this radius R? Can that help you get more torque? Okay. Or if you push harder, right? So if you increase the R, increase the F, okay? And then also make sure that you push perpendicular. That's like maximizing the sine theta. Right, so all three of the, so all the above. Yeah. Oh, I got Ella, Isabella, Spencer, Anna, Bruce the villain. Football is kicked so that the force is through the center of gravity. Okay, yeah, it's just not gonna tumble or spin. As long as you hit it through the center of gravity. COG stands for center of gravity. Okay. So yeah, I have another activity for you guys related to this, but here's the idea. Here's football. Okay. And then here's the center of gravity football. It's probably also a geometric center. It's a symmetrical looking object. Okay. What if you kick it? There's somebody's kicking foot. Like right, bam, right through the center. Right. Now the whole football will take off. Maybe like that direction. Right. But why would it tumble? Is it going to go clockwise or counterclockwise? Well, neither, because you're kicking it right through the center of mass, center of gravity. All right, so that's all there is to that one. Resistance an object has to change in its rotational state of motion. Remember I passed around those 2-meter sticks? Right there. Still over there by that wall if you want to get your hands on them. What was that? Yeah, rotational inertia. There you go. Right. That's exactly what that is right there. Rotational inertia. Okay. And then, of course, a lot of these rigid rotating objects have been worked out ahead of time. Okay, so I've got a whole table of values right there. Yeah, rotational inertia. There you go. Yeah, Isabella, Ella, Anna, Spencer, Bruce the villain. Which has more rotational inertia? A bicycle wheel or a solid disc? Say have the same mass, the same diameter. One winner. One winner. Wheel.
That's me.
Yeah, yeah. All right. Winner. Okay. Guys, the answer is right here if you compare these two. Right. Here's the wheel. Here's the solid disc. Okay. Maybe this is both like rotating about these respective central axes. Yes, yeah. Okay. And so for the ring, if you take the again, if you put these two objects both on scales individually, the scale reads the same weight because they have the same mass. Okay. But the ring, you get mr squared worth of rotational inertia. Same as a point mass. Right? You just add a bunch of point masses, becomes a ring. Right? But the deal with the solid cylinders, you guys see how a lot of the mass is distributed more closely to that central axis? Right? Like not all the mass is like at the radius r. Right? A lot of it's closer to center, which means you don't get as much rotational inertia. So generally, so this would be less. Right? And if you do the math on it, it turns out to be exactly a ratio of half of one, 2 to 1 if you go the other way. All right. So the wheel has double the rotational inertia of the disc. Ella, Anna, Spencer, Nicholas, Bruce the villain. Which has more rotational inertia? A runner with who runs normally with their legs bent, or what if you keep your legs straight, like you don't bend your knees at all? More rotational inertia. So more gets more inertia, more inertia. Right. So if you think more in terms of like this right here, somebody with MR squared, right? See if you keep your legs straight, like you don't bend your knees at all. Right? Maybe your legs are extended. Maybe it looks kind of like this picture, right? Actually, something like that. Your leg work. But if you bend your knees, aren't you moving your feet closer to your own center of mass? It's like moving this mass closer to the axis of rotation. That's like decreasing this R right here. You see that? Right? Guys, can you run faster if you actually run normally?
Yeah.
Yeah. Okay. Because if you ran like this, okay, one reason that would not be helpful is because you'd have so much rotational inertia in your legs, it'd be hard to change the same motion of your legs since it'd be really hard to run. Okay. Like more inertia means it's more difficult to change your motion. Any solid cylinder will roll down an incline with greater acceleration than a hollow cylinder. What? Panther is right over there on the wall. One says roll race. All right, so the idea is that the solid cylinder will always be the ring. Okay, and okay, it's like this. So actually, this is one part we haven't quite got to yet, but see if you guys can figure it out or reason out or think about it. Okay. So let's say we got all these rolling objects rolling down this incline that has some static friction with the object. Okay. With one exception, I do have a hockey puck, like an air hockey puck here, with no friction at all. Okay. Now this is going to slide down, and I know the speed at the bottom is going to be square root 2gh. Again, that's just for the hockey pucks. Okay. And that's gonna, like, if you have a race, that's gonna beat all these other objects. Now, all these other objects, some of the energy goes into making it rotate. That's one way to think of it. Oh, actually, I have a solid ball here, right? So here's the solid ball version. Okay? So if you want to say, hey, what's the linear speed at the bottom? That's a classic question. But there's a process you can go through. This is using an energy method to get the answer. Okay? But the idea is that has to do with how the mass is distributed. So do you guys see the like if you go from left to right with these objects, it also rank orders them in terms of mass is distributed closest to the center for the bowling ball. It's spread out a little bit more for the solid cylinder. It's spread out a bit more for the spherical shell, like a basketball. Okay, and the mass is distributed furthest out mathematically with the ring. Okay, if these were all equal masses in equal radial sizes, that'd be a pretty easy comparison. Okay, but it turns out that even if they're different masses or different radial sizes, that variable cancels out. So, like if you had two cylinders, hey guys, let's say I put both of these at the top of an incline and let them roll down. Now these are both basically the same shape. They're both basically solid cylinders. Would these tie? Different radius, different mass. Yeah, because they're both solid cylinders, so they would tie. Right? So really, who wins the race has to do with how the mass is distributed at the end of the day. Right? And so yeah, more details probably on that in the next few days. Planning. We got Anna, Gryffindor, Nicholas, Spencer, Bruce the villain. Gymnast moves from extended to a tucked position. Ooh. Yes. Decrease rotational inertia. Okay. And so here's the figure skater version of that. Okay, so here's Winter Olympics. Question you guys got with Summer Olympics, but same idea. Okay. You go from an extend position to a tuck position. Okay. You are bringing your mouse in closer to the axis of rotation, hence you are decreasing your rotational inertia. Okay. Now another consequence of that, of course, is that if you're rotating, it'll actually cause you to also rotate faster because of conservation of angular momentum. So there's a little extension idea. Okay, any questions on any of these so far? That's right. All right. Got Gryffindor, Ella, Nicholas, Stavellin, Spencer. Ice Skater pulls his hands in to turn faster. Ooh. The angular momentum must be conserved. Maybe the moment of inertia decreases, the rotational speed increases. Yeah, all the above. All the above. Okay, isn't that exactly that right there? Same idea. Boom. Yeah. That's what saying it. You got Bruce, Ella, Nicholas, Spencer, Bruce the villain. Oh, large rotating cloud in space shrinks in size and rotates how? Yeah, that is the same as this all. Here we go. This all over again. Okay. So if you have a giant nebula out in deep space, right, closed system, right, you got all these particles, right, space dust particles, right? They're gravitationally attracting. Let's say they're slowly swirling together, right? Well, as they attract together, the rotational inertia of that whole cloud system decreases, and so yeah, they're going to actually spin faster to maintain angular momentum. Angular momentum. Nice. Got Anna, Ella, Nicholas, Spencer, Bruce the villain. One person leans toward the center of a seesaw. Okay, so back to torque questions. That person's end, Will. This person leans towards the center. Yeah. Okay, most of you guys got that. There will rise. Okay, you can back it up with this. Right, so it's torque is r cross f. I'm gonna draw this out. So let's get a seesaw going. Right. And a couple of friends. Put one friend here, one friend here. Okay. Let's say the same mass, same weight, same distance from the center. Right. Wouldn't this be in equilibrium? It'd be balanced. Right. So let's look at this in terms of torque. So relative to this pivot point, I see some radial arm crossed with some force. Here's the force down here. G. Okay. Okay, here's radial arm R. Okay. And that's resulting in a counterclockwise torque. Call it tau for torque. Okay. Well, this guy on the right side, he has also distance R over here and weight mg, okay, and causes a clockwise torque. Okay. So right now everything's still balanced, right? Okay. But what if I make a change here? Let's see a new picture. Okay. No, it says the person leans in was the question, but you can always exaggerate the effect, or oftentimes that's a good trick to do, right? And then it makes something even more apparent. Right? Now these guys' weights didn't change at all. This guy still weighs mg. This guy still weighs mg. That didn't change. Right? Right? But this is a small lever arm, which results in a small torque. This is a large lever arm, which is same large torque as before. Right? So you guys get this whole system. This going to end up rotating clockwise. In this case, like clockwise, like that. Okay, so if you're the person who leans in, your end will rise. There you go. Explanation there. Got Anna, Spencer, Ella, Nicholas, Bruce the villain. To turn a stubborn screw, best to use a screwdriver that has a ooh. Guys, this is a screwdriver, not a wrench. A screwdriver.
Yellow pin.
Stubborn screw.
What?
Hurricane.
Yeah, wide handle. All right, pretty good. It trips up a lot of students every year, but not you guys. So here, I'll try to mention you guys why. Okay. So let's say here's a screw, my stubborn screw, and then I'm gonna use a screwdriver right here. Try to pull this out. All right, here's my handle, like this. Okay. So I'm gonna wrap my hand around the handle and start turning this way. Okay. Now I remember here just to contrast this a little bit. Okay. With the wrench, which is a different question, isn't the axis of rotation right where my finger is? Is the axis of rotation? It goes out of the page, and we're rotating around that. Okay. That's different for the screwdriver. For the screwdriver, your axis of rotation is right here, this dash line. Okay. And if that's your axis of rotation, I'll call it axis. Okay. Then the radial arm is actually this R here. Which has to do with the width of the handle. Okay. Like if the width has some diameter, half that's the radius. Okay. And then if you wrap your hand around there, do you guys think there's some friction between your hand and the wrench handle? Okay. Hey guys, what if you do this? What if you cover this handle in grease? Cover it in grease. Does that help you or not help you? Yeah, that would be incredibly not helpful. Right. But what if you had a really dry handle? Right? That would definitely be helpful because you're getting more frictional force. Right. So there's this force that's perpendicular to this radial arm. Okay. Right. And you get a turning moment. Yeah, so something to do with the width. Right. So if it's a wrench, you want a longer wrench. If it's a screwdriver, you want a wide screwdriver. Ooh. All right, Anna, Nicholas, Spencer, Ella, Bruce the villain. Ring and a disc roll down the hill together. Who reaches the bottom first? Right, you can see in a class right over there. Ring and a disc. So the one says roll race. Yeah, the disc. Disc will always beat the ring. Okay. So, so we're looking at here. Here's the disc versus the ring. Again, the individual masses and radial sizes end up canceling out. Yeah, I showed you guys the bowling ball. Do I have? Okay, I do have a ring here. I forget if I made a disc. Let me see if I. No, I don't think I made a disc one. Okay, but well, okay, you guys can see the ring anyway. Anyway, there's a process, and it turns out that the mass and radial size of the ring end up canceling out. Okay, it's actually true for all these Rolly objects. It has to do with how's the mass distributed. Okay. Yeah, so this beats a ring. There you go, Oliver. Got Ella, Anna, Nicholas, Spencer, Bruce the villain. Good explanation for why a ball gains speed as it rolls down an incline. It involves. Uh, okay, yeah. You do need a little bit of all the above. Right. Some of the, maybe it's weight could be the force X on it. You do need a frictional force to cause rotation, and causing rotation causes a torque. Right. Let's look here. Right. So here's another ball rolling down a hill. I have two different explanations to answer the question, what's the speed at the bottom? Right. Now, normally in class, I tend to do the energy explanation. Right. You can get the linear speed. This is, if you point a radar gun at it, at the bottom ends up being this. Right. Right. So here I have both these ready to go, so I'll just look at the basketball. Right. Now there is a different type of explanation, which is a different process, which results in the same answer, right? But it goes through forces and torques rather than energy. So it goes like this. There are three forces properly on anything rolling down an incline. Okay? There's its own weight pulling it straight down the center of the earth. There's the normal force perpendicular to the surface of the incline. That's what normal is. Right? But you also need a frictional force to induce rotation. Because if I did not have this friction force here, would this ball even roll at all? Like what if no, it turns out it wouldn't. Turns out it wouldn't. Right? So if you had a like an air hockey type table that you were tilting up, right? And you set something on top of it, it's kind of levitating. Right? then it would actually look like a knuckleball. It wouldn't even roll at all. I mean, it would kind of slide down, it would accelerate, but it wouldn't actually roll. Right? Because these other forces each go through the center of the object. Right? Yeah, so you do need a friction force to induce rolling. Oftentimes you'll see it phrased like rolls without slipping, or yeah, rolls without slipping. So they'll make it a static friction force. Nice. All right, Ella, Anna, Spencer, Nicholas, Bruce the villain. At different orientations, the cams provide different. Right, there's a cam. Now, as this rotates, ooh, let's put that emotion in your mind. Different lengths of lever arms, different forces required to produce given torque. What do you think out here? As that rotates, yeah, it would be both of the above, both of the above. Okay, because as it's changing orientation, yeah, the lever arm would change. Okay, if you were targeting a particular torque, you'd have to pull it harder or less hard to do that for different lever arms. Yeah, both the above. I, I got Ella, Nicholas, Anna, Spencer, Bruce the villain. You pull the string, the spool will move. Ooh, you guys remember that spool I pulled out the other day? Guys, let's say the table down here is at the bottom. There's some friction with the table down at the bottom. You pull to the left, it moves to the left towards you. There you go. Right, moves towards you. Right. Pull to the left, moves to the left. Right. Ella, Anna, Spencer, Nicholas, Bruce the villain. Right. I think I'm gonna change the picture here. Right. So same thing as before. The table surface is down here. Pull to the left. Yeah, still goes to the left. Here, let me convince you guys this is true. Yeah, dig up this old demo here. There it is. All right. So I got that right here. Get rid of all this. That's here. Okay. All right. So here's my spool right here. Right. Okay. Oh, here I'm gonna turn this. Well, actually, here the last couple questions. You guys saw one where I was pulling this way to the left, right, and then it would roll to the left. Okay. So just torque that way. Okay. And then the question you guys just had is, what if I flip this upside down like this, and I still pull to the left? Does it still roll to the left? Yeah, sure does. Sure does. See that? Pull the left, it goes to the left. Here's that. Okay. And the idea is that it's not actually rotating about the central point. It's actually rotating about this point down here, where there's friction with this table surface. Friction with the table surface. And that's inducing a torque, which overall makes it rotate. Well, from my point of view, I would say counterclockwise, like that. So, there you go. Right in there. Ella, Spencer, Anna, Nicholas, Bruce the villain. Where should a 30 Newton weight be placed so that the meter stick will be balanced at the 50 centimeter mark? Ooh, sounds like a lab you guys just did. So here's a 10 Newton weight, which is, guys, is the 10 Newton weight 30 centimeters from the center? So where would you put a 30 Newton weight to balance that out? Okay. Here we go. Oh, okay. Some of you guys said 60 centimeter mark. We convince you guys that's true. Okay, so here's the setup. This weight was 10 newtons. So I'll say weight equals 10 newtons. Okay. And that was at an offset distance, well, from the pivot point. I'm going to sum the torque about this pivot point. I think it's the most intuitive point anyway. At least way to do this. Wait, was this 30 centimeters? I think R equals 30 centimeters. Okay. Yeah. So, huh? Is it at the 20 mark? Right. Yeah. So 50 minus 20. That's where I'm getting 30, right? 50 minus 20. Okay. So that's resulting in this counterclockwise torque of R cross F. Is that 30 times 10? Is that 300 Newton centimeters? Right. And that's clockwise. Right. Clockwise. A lot of times you call it negative for clockwise. Right. But now I'm going to have a weight that's 3 times as much. Well, 3 times as much weight. So let's see. I think I'm going to hang this probably about here. Okay. So if this weight here is like mg equals 30 newtons, okay, shouldn't I have it at an offset distance radial arm of like 10 centimeters?
No.
Like that? Okay. So it produces a clockwise. Oh, wait. What am I saying? Sorry, the other one was counterclockwise. So which would be positive. I don't know why. Sorry about that. So the other one was positive 300 Newton centimeters. This torque has to be the clockwise, which is negative 300 Newton centimeters. Okay. And the only way to get that is to have this be a 10 centimeter arm right here. So 10 times 30 is 30 times 10. Right, guys, yeah. So it balances out. Right. Okay, so what mark location is that? Well, if the center point is at 50 centimeters, then the answer is the 60 centimeter mark. Guess that? Okay. You're kind of like the lab guys did last week. Okay. Hey guys, I got a follow-up question for you guys. How much normal force is being supplied from this pivot point right here? How many newtons up is this? Can anybody figure that out?
Maybe not one.
Okay. Like guys, if you balance this on your finger, you hold some weight, right? You're holding up some weight. How much weight do you have to hold up?
No, 40.
Yeah, 40 newtons. This is pushing up with 40 newtons. Yes, yeah. Okay. Or if you held this from a spring scale, actually, that's what you guys did last week, didn't you? You hold this from a spring scale right here. Okay. And the spring scale could read 40 newtons. Yes, that. Okay. And I say all that because, well, it's good to be able to figure that out anyway. Okay. Is what if I do this? What if I sum the torque about any other point? What if I sum about this point right here? Does the torque still sum to zero relative to this random point over here? Yeah, I bet it will. Here, I'll do the calculation version. So I'll do this all on the calculator screen. So I'm going from the 0 centimeter mark. So that's 10 times, this would be 20, wouldn't it? Right here, 20. Okay. So, well, let me do R cross up. So I'll do 20 times 10. Okay. And that's clockwise. So I'll call it clockwise negative. So times -1. Okay. Then this pivot point holds up with 40 newtons at the 50 centimeters. So plus 50 times 40. Okay. And I'll do minus for another clockwise. This is at 60 centimeters out now. 60 times 30. Okay. Guys, when I hit enter, my calculator has to tell exactly one number. What number does it have to say? Guys, what is... Okay, so I switch my pivot point to this random point at the end of the stick. So I have this clockwise, this pivot's holding up counterclockwise, and this big weight's pulling back clockwise. But the sum of the torque has to be what? Zero. Boom. And it is. It's zero. You can pick any point on the in that system and it'll zero out. Okay. And you guys did that too last week. Okay. You guys remember you had identical setups, but you just switched your defined pivot point. So, all right, we got Ella, Anna, Spencer, Nicholas, Bruce the villain. In order to increase rotational inertia, a tightrope walker can carry a long stick. Ooh, is that why they carry a long stick? Increase their rotational inertia? Yeah. Okay. Does that help you balance too? Help you balance? Yeah, it's probably why they carry a long stick. Okay. You guys ever try to balance maybe like on a game and you hold your arms out like this? Hold your arms out. That helps you balance too, right? Okay. And that's actually what you're doing. You're increasing your rotational inertia. So if you get off balance a little bit, you start to fall. Well, your fall is delayed, right? Because you have so much more rotational inertia, and it's easy to correct your position. Yeah, so you can maintain balance easier. Yeah, that's what that's about. Right? So if anybody asks you, like, yeah, why is it that when you balance, you hold your arms out? You say, oh, well, you increase your rotational inertia, obviously. Short pendulum has more rotational inertia than a long pendulum for the same mass. Is that right? MR squared. Guys, you guys know what a pendulum looks like. Right, TikTok. MR squared. Yeah, I think it's the question is framed exactly backwards to the truth, isn't it? Yeah, like if a longer pendulum, right? Okay, should have a more rotational inertia. It's MR squared, right? Oh, was that? Oh, that was the last question. So podium with the bronze, got Spencer with the silver, Nicholas, and the gold, Bruce the villain. All right, nice job. Nice job. All right, so yeah, we got a few minutes. Let's knock out some more of these textbook puzzles. Okay. So back on Friday, we did do these two. Okay. Let's do, how about 94 hard drive? That looks fun. 94 hard drive. Let's start this one because we'll do this one today. Okay. I think this is a kinematic question. Yeah, this looks kinematic. Okay. So it says a hard drive on a modern computer spins at 7,200 RPM. You guys ever heard RPM? Oh, yeah, go. Yeah, here, there's a second one. Here. You got it. Yeah. So that's revolutions per minute. Okay. Now already, guys, already I'm thinking if we're gonna apply equations, should we turn that angular velocity to what unit? We don't want revolution per minute. We want what per what? Yeah, radians per second. Okay. Okay. So whatever numbers I feed in the calculator has to be consistent with base SI units, especially angular velocities, that kind of thing. Radians per second. The drive is designed to start from rest and reach an operating speed in 1.5 seconds. What is the angular acceleration of the disk? Angular acceleration. That makes me think of these right here. Here's your kinematic formulas in a rotational context. Same for a turntable. Okay. Here's your turntable. How far the turntable turned, that's what theta is. How fast it's turning is omega. Okay. And what they're asking about is angular acceleration, which has to do with what rate is it speeding up spinning. Okay, so that's what we're doing here. Okay, so you guys writing this down? Because I'll have you guys eventually turn this in and give you guys points for doing it. Okay, so 94 we're doing. 94. Okay. Here, I'll draw you guys a picture. So here's your hard disk right here. It's going to be spinning. Oh, error. And we're going for, I'll say omega final. So the target angular velocity is 7,200 revolutions per minute. Okay, that's how they gave it to us. Okay. Let's have omega initial be 0. I'll say radians per second because we'll eventually go everything radian per second. Okay. And we're looking for a time interval, say t or delta t if you like. It could be 1.5 seconds. Okay, so given all this, the question is what's the angular acceleration during this 1.5 second interval? So it builds up to this speed. Okay. All right. So let's convert this RPMs to radians per second. I think I can do that in a couple steps here with some railroad tracks. You guys are doing this last semester quite a bit. A little unit conversion here. Unit conversion. Okay. Did you guys use the same method in chemistry too? No. So here, guys, show hands. How many guys saw this particular method in chemistry? Okay, yeah, maybe about half you guys, but not everybody. Yeah, that's where I learned this. Anyway. So how many revolutions and how many radians? Whatever what? Yeah, 2 pi radians in a revolution. Yeah, 2 pi over 1, exactly. 2 pi radians is equivalent to 1 revolution, okay? Like one complete rotation. You could also say 360 degrees, although that wouldn't be helpful here, but it would be equivalent. Okay, so now I have radians per minute, but I really want radians per second. So what else do I have up here? Whatever what?
Sorry about.
Yeah, 1 minute is equivalent to 60 seconds. Now the only units on the board are radians per second. So let's just feed this into the calculator and get the target angular velocity in radians per second. So 7,200 times 2 pi, right? And then divide by 60. I'm looking at 753.98. I'm just going to call it 754. That's radians per second. Yeah. All right, you guys got that too? Look about right? Okay. Okay, so we have a target angular velocity. We're starting from rest, and this is all going to happen in this time interval. Okay. Question is, what's the angular acceleration? Like, how fast is it speeding up? Okay. Is which formula? I'm in trouble fitting this all on the same screen here. Okay. Is which formula, first, second, or third, is going to be able to answer that question? You saying the second one? Yeah. Okay. So Anna's saying the second one. I like the second one too. Okay. Here's why. Because we know these and this. Right? We're solving for this, so it's all there. It's all there. Okay. The first one tells you how far it's rotated, which they didn't ask for. Okay, and kind of same problem with the third one. Okay. But I like that second one. So let's do that. Let's do how fast it ends up spinning is equal to how fast it started spinning, which of course is 0. Okay. Plus alpha times t. Okay. You guys remember one of your first big labs? You guys had speed gates and stopwatches and well, some of you guys, I had split you guys up into different groups. Okay. So that was kind of the linear version of this rotational example. And so here, I'm going to go call this 754. That's radians per second. And it's equal to alpha we're solving for times 1.5 seconds. Ooh, one algebra step to get the answer. Because what's the last algebra step? Yeah, divide by 1.5. 754 on 1.5. Okay. I'm looking at 502.67. I'll just call it 503. That's radians per second squared. Okay. So while it's spinning, it's spinning for about a second and a half. It's picking up 503 radians per second per passing second. Looks like that. You do some other calculations with that if you like. So working away with it. All right, you guys get there?
Not yet.
Almost there.
Awesome. Thank you.
All right, let's do one more. One more. Yeah. No.
Okay. Thank you.
Okay. Yeah, so last one. Let's do right beneath it, number 95. I'll start that one because we're doing those together. Number 95. Speedometers. Most speedometers in automobiles. Okay. Like, guys, if you drive your car and you look at your dashboard, it says, oh, you're going 45 miles an hour. Okay, that must be my speed. How does the car know? And it's going to say right here. It says, really what they're doing is they're measuring the angular velocity of the transmission. And they're converting it into speed. And the question is, how will the increasing the diameter of the tires affect the reading of the speedometer? So let's get a picture going. So this is 95. Right? So let's say I have a car. Right? It's like a regular car. It's regular tires. Right? And I drive it and it tells me how fast the car's going. Then I think, hey, you know what? I'm tired of these regular tires. I want giant monster tires. Oh yeah. Oh yeah. I'm getting some monster tires on my car. Right. Now, you can't just pop this on and expect the speedometer reading to give you an accurate reading for how fast you're going. Okay. Like here, guys, suppose this car over here says, oh, you're going 45 miles per hour. Okay. I could probably trust that reading. Okay. But guys, over here, if the speedometer reading still says 45 miles an hour, are you still going 45 miles an hour? No, because when this wheel makes one rotation, has your car moved further or less far than this car that also makes one rotation? Further. Yeah, a lot further. A lot further. You guys see that? A lot further. Right? So, again, keeping in mind how the car's like internal clock is kind of working, right? Its internal speedometer, right? It says, oh, well, if one rotation in some interval of time corresponds to 45 miles an hour, right? Then over here, if the car's actually gone much further during that rotation, then if the car's saying 45 miles an hour, how fast is the car actually moving? Slower than or faster than 45 miles an hour? Faster. Yeah. So a cop over here points a radar gun at you. Maybe this radar gun says you're going like 90 miles per hour, which is actually what you're doing. But your speedometer says, oh no, I'm only going 45 miles an hour. The cop says, no, you're going like 90 miles an hour because you're monster wheels. I guess that. Okay, and that's related to this formula, V equals omega times R. Okay. So, oh, Yeah, so like one complete rotation, uh, with a larger radius means the car is going to propel faster than the speedometer reading would be rated gauge. Okay. All right, so well, anyway, there's a verbal explanation. That was about ring, so let's close that up right there.